The supply and demand of electricity can change very suddenly, such as the power from a solar farm when a big cloud drifts overhead. So in order to keep the grid stable, engineers must build systems that can respond rapidly. Inventor Peter Frankel is a pioneer of renewable energy, creating novel wind turbines and the world's first commercial-scale tidal turbine. So he's well-placed to understand the need to solve this problem.
I decided I'd like to get into energy storage, and I was looking around for some clever way of ideally using mechanical engineering of storing energy.
Peter was fascinated by the mechanism inside a grandfather clock in his home similar to this one, a family heirloom.
Basically, it has some very heavy weights, and those weights, under the influence of gravity, would like to fall down, but they can't because they're hanging from wires connected to the mechanism. So if I put the key in and wind the handle, this slowly raises the weights, and the energy from my muscles goes into the weight, and the weight then will be energized, basically, and ready to return the energy to the clock. This clock is 300 years old, and actually you could leave these weights for another 300 years if you did nothing else, and no energy would be lost. But if we start the clock, so the pendulum swings, now the clock has started to tick, and both the weights, in fact, will slowly descend. So, you know, it's an incredibly durable form of energy storage.
Peter's idea was to scale up the mechanism in a grandfather clock to store huge amounts of energy. To be a success, it would have to respond in under a second. To turn the concept into reality, Peter founded Gravitricity. He wanted to build energy storage units underground. Peter appointed engineer Miles Franklin to oversee the project in Scotland, as he had to self-isolate in London.
To store a lot of energy, you need either a lot of mass or a lot of height. So in order to get to very interesting levels of energy storage by lifting masses, it's good to go down. It's also then, once it's underground, it's hidden. So you could do it under a city, under a football pitch, wherever you liked, in order to store energy, and then without having problems with wind and weather and all these other things. And so we started to look at both existing mine shafts that are no longer being used for mining, and also the idea of sinking new shafts specifically for energy storage.
Before going underground, Miles was in charge of building a tower prototype to prove it could provide power rapidly. The team filled 2 steel containers with over 50 tons of high-density ballast. This would store energy when lifted up and release it when lowered down. The 30-foot tower was then lowered onto the containers and secured.
There was some, scary moments along the way when we're moving very heavy things and lifting them, so there's a sigh of relief when they're all in place.
Once it was all assembled, they were ready to store energy for the first time.
We got to the moment we were going to lift the weights. We had quite a lot of the engineering team on site. So yeah, there was some tension.
They used power from the grid to raise the weights and charge the system with energy.
For that lift, it's the first time that the whole structure is supporting the weights. And you'd expect, as you lift, some strange noises as the structure kind of finds its place. When the weight reaches the top of the tower, the system is fully charged. We can stop, we can pause, we can hold that energy for as long as we want.
But how fast can they return power to the grid when it's needed? Senior test engineer Jill McPherson knows how important that is.
Right now we're going through a transition from using fossil fuels towards using renewable energy to generate electricity, but that means that the grid is less stable. With conventional power, we have these big generators that provide a lot of stability to the grid, but with renewable energy devices, they don't really provide that. Sure, we wanted to be able to go from 0 to full exporting power within a second so that all the devices on the grid can operate safely.
All systems are go.
To generate back to the grid, the weight is lowered, the weight pulls down on the steel rope, which turns the winch, and then via the gearbox, turns the motor. The motor acts as a generator, so then we're putting power back into the electrical cable via the power electronics straight into the grid.
The tower had successfully generated electricity, but for the first few seconds, the power supply had fluctuated too much.
And so what we find is when we accelerate really quickly, the weight starts to bounce up and down, and that bouncing weight becomes a variation in the power. So what we need to do is find solutions to be able to accelerate really quickly, but then have that power output from our system quite smooth. So we need to try and find some way to fix that.
The team must find a solution to generate a smooth power supply more quickly when the weight starts to drop. Although the concept may seem simple, smoothly lowering a weight of 50 tons in a fraction of a second involves intricate mathematical modeling.
Analyzing the dynamics of the weights and the movements and then designing them is actually quite complex. And so that was something that took us a while to get right.
1 month later, Miles and Jill have a plan.
We're testing.
After many simulations and tests,
It's clear.
they think they've figured it out.
Okay, so 3, 2, 1, go. If we want to go from 0 to full power but have smooth power at the maximum power, then what we could do is apply a force that cancels out the tension oscillations in the cable, and then that corresponds to smoother power. Right.
To find out if it produced a useful source of power in under a second, they must analyze the results.
In this last set of tests that we just did, you can see that the power is much more smooth. It's a straight line, and that's what we're looking for. We went from 0 to full power in 0.96 seconds.
Gravitricity's prototype has proven it can respond rapidly to the demands of the grid, a significant improvement over pumped storage, which can take minutes. In July 2021, Peter Frankel was eventually able to make the long journey from London to Scotland to see the tower for the first time.
A bit better than the grandfather clock, yeah. It doesn't have such a nice face on the top of it, but yeah.
Now that this prototype has proven his theory, Peter has big plans for the next stage of his energy storage system.
In the near-term future, I think we're looking at, initially systems a few 500 meters deep and 6 meters diameter. So it's like a railway tunnel turned on it, vertically. We hope and expect that gravity-based energy storage of the kind that we're trying to develop could have a massive impact in terms of facilitating the wider use of intermittent renewables.
A typical system would store enough electricity to supply 13,000 homes for 2 hours. Gravitricity hope to build their underground mechanical batteries all over the world to store green energy. Meanwhile, back in Switzerland, a startup called Energy Vault are building another type of gravity battery. The goal is to store energy as cheaply as possible. CEO Robert Picconi understood that the only way to move to 100% renewable power was to undercut the price of electricity generated by fossil fuels.
You have to be able to essentially compete with something that's about 5 to 6 cents a kilowatt hour. And the good news is solar and wind now is just a few cents, 1 to 2 cents a kilowatt hour. So the economics really work there. You therefore have to target storage that must be between 3 and 4 cents to have something that at least is on parity with fossil fuel, and therein lies the challenge.
To meet this challenge, the team came up with a specific design. The Energy Vault 1. A crane with 6 arms that could lift heavy bricks and stack them on top of each other to store energy. Then, to release that gravitational energy, the cranes lower the bricks back to the ground one by one. By building a tower made of thousands of heavy weights, they could store large amounts of energy and therefore bring down the cost. And by using mostly tried and tested machinery, they could build it quickly. But first, they had a thorny issue to tackle. So they built a quarter-scale system to try and find a solution. The problem is that when heavy objects are lifted by a crane, they can swing like a pendulum.
One of the main challenges we have in utilizing the system to move large objects is the environmental impacts on that object in movement. And it's a very important problem when you're moving large things like containers, for example, that are at the ports, and when the cranes are moving them, they will sway and impact the ability to precision place them. When we're moving around 35 metric ton bricks that we have to stack at height, it's very important that we be quite precise with that. And so that was one of the major challenges, was to solve for this pendulum effect.
When the trolley on the crane moves along the arm, the weight below starts to swing back and forth, making it almost impossible to precisely place the weight in its new position.
We had actually thought that the crane industry had solved this already for the movement of things in the ports and these large containers, but as we talked to other partners and suppliers in the space, it hadn't been solved, and so we had to develop the algorithm for that ourselves. And it's a very important algorithm because it's not only necessary for the precision placement of the brick, but also to deal with any unpredictable weather events, for example, a high gust of wind. So this was fundamental that we use software to solve this. So we took concrete barrels and utilized an existing crane that we modified to test the ability of software to cancel this pendulum effect.
As the test began, an AI control system could predict how the weight was about to sway. It then instantly adjusted the movement of the trolley to cancel it out with an equal and opposite motion.
One of the most fascinating things is to focus up on the trolley and to see the back and forth movement in light speed so that concrete barrels maintained that consistent velocity. And just amazing to see that software at work and manifest itself from the modeling to reality.
In January 2021, work began on building the full-size crane. But this would be nothing like the cranes you might see at a construction site. After laying extremely strong foundations, the team assembled and secured the 7 sections that made up the 660-foot high tower. In the meantime, another team assembled the 3 rotating platforms called jibs.
Just one jib of the crane weighs 130 tons. So just to construct it is one thing, but then to maneuver it around the site, we had to use a special horizontally designed hovercraft system that could maneuver and shift from the shelter where it was constructed to a location where the crane then, the 600-ton crane, could be attached to that system and be able to lift that jib up so it can be constructed onto the crane itself at height. Just fascinating and amazing, and just a great job by the team to pull that off.
The crane stacked the jibs on swing bearings on top of each other so they could turn independently. Once in place, it was time to assemble the arms which support the transport trolleys.
Having enough arms of the crane with enough megawatt motors per arm, you could generate up to 5 megawatts of power and be able to essentially discharge that over a period of time, at least 6 hours, but ideally up to 8 to 12 hours, in a way that could be reliable.
While the multi-armed crane took shape, Rob faced a dilemma over how to make the 40-ton bricks in a way that was both cheap and environmentally friendly.